Okay, recording in progress. Hi everyone, welcome to the Hitchhiker's Guide to Rheology. So today we are welcoming Francisco Rocha. I hope I'm saying it right. Can you just put the page, Michelle?
Yes, sorry.
Thank you. So he's a postdoc at Aix-Marseille University, and he's going to talk about dry granular flows, and especially like self-organization and instabilities of them. We're really happy to welcome him today. And Francisco, if you might share your screen and also talk a bit about what is your history? What did you do before? What was your PhD about? Where did you do it? Where do you come from and why rheology? Why are you studying that and why are you going towards that? Are you still going into the academics in the future and so on? It's already so many questions. You can start to share. Sorry.
Allow me to present us. Yes, I do
Yeah.
allow. Up. Share. So I guess you can see my screen now.
Yeah.
It's okay?
Perfect.
Perfect. So let me just hide this floating stuff. Right. So if I start with all of these, so I'm Brazilian and then I did my master's, bachelor's, everything in Brazil before I moved to Manchester. So I did my master's in fluid mechanics, more specifically in hydrodynamic instabilities, Saffman-Taylor instabilities, and it was very theoretical work.
Yeah.
And then I moved to the University of Manchester to do my PhD, which I will show you a bit today.
Okay.
And for me, it was amazing, this abstraction, let's say like this, to interpret and to describe granular materials where you can see the individual constituents
Yeah.
with a rheology as an effective fluid. And that's why this continuum kind of approach works so well, in a sense.
Mm,
So this was what drove me to these granular flows.
okay.
And then, as I hope to show you today, these are incredibly efficient to produce amazing patterns. And for me, I do fluid mechanics and all these more because of the beauty of the patterns and instabilities than other things. I hope people understand.
Oh
But
wow. You're really
so this
passionate
is
about it.
it's more or less this. And so I'm here in Marseille now, and I hope I can find a permanent job in soon, as you asked.
So still in academia, still doing rheology. Oh wow.
Yes,
Okay.
yes, yes.
Very nice. Um, okay, so uh, actually, like Francisco is okay with you asking question during the talk, so you can raise your hand, and we can even read your question in the chat if you're a bit shy to say it out loud. But yeah, Francisco, you can start. Thank you again for coming.
Cool. So, okay. So, first of all, good afternoon, good morning, good night. Depends on where you are. I'm Francisco Rocha, so I'm here at UST, as I said. And so, as Leia said, you can ask questions whenever you want during the talk. I prefer to not get to the end, but that we can discuss as much as we want. So the story I would like to share with you today is about dry granular flows. So it's a work that I've been doing since my PhD in Manchester. And more specifically, I would like to discuss how to characterize the rheology of these granular materials and how this peculiar rheology can lead to kind of very interesting self-organization and instability patterns, such as this one that I'm showing you here, which are just dry flows of just sand flowing down an inclined plane. So let me start just for self-consistency reasons. What is a granular material? So I would say that generally speaking, the granular materials is just a mixture of solid particles in a fluid. This fluid can be air, water, or any other viscous fluid, where the particles has the properties, so diameter d, the density rho s or rho p, and the surrounding fluid has a viscosity eta and a density rho. And the ratio between the volume of grains to the total volume of the mixture is generally called the volume fraction phi, right? So you didn't say anything, but I agree with you that this is a very loose and wide definition. So this makes granular materials kind of widely seen in many different scenarios. Typically, granular materials are widely observed in large-scale geophysical flows, such as debris flows, pyroclastic flows, snow avalanches, landslides. And normally these involves a huge mass of grains that can be in a solid state, and for some reason they are fluidized, for example, in this mountain here, in Mount St. Helens. And what these flows they do generally is that downslope after these the fluidization of this granular mass, this generates a very dense flow of this mixture of fluids and particles. And these flows, it's quite important that we understand and we can predict how these mixtures flow, because they are quite destructive flows, so they are quite efficient in transporting mass. And so to mitigate the destructive potential of these flows, it's important that we understand how to model and how to understand how these things flow. But also these granular materials are widely seen in a wide range of industrial sectors, such as civil engineering, food processing, paints, bulk chemicals, and everything. So there is a quite important economical motivation to study granular flows as well. In a scientific point of view, this is a subject that has been kind of attracting the attention of many different communities: statistical physics, fluid and solid mechanics, soil mechanics. And I would say that this is mainly because these are not trivial systems to model with classical techniques. And some reasons for that is that these granular flows, they are in many situations are thermal, so they don't feel thermal agitation, and they are extremely dissipative. So particles interact by collisions, inelastic collisions, such that it's not so easy to use classical statistical mechanics to describe them. And also in a simple scenario, such as a spoon of sand, there is a huge amount of particles, such that it's quite difficult to track these individual particles to know their trajectories, for example. Another thing that makes these systems quite intriguing is that they can behave as a solid, as a liquid, for example, in these avalanches, or in a sandstorm like a gas. And in a typical situation, real scenario, they can behave in a coexistence of states. So you have the gas, the liquid, and the solid state coexisting in the same flow. So in a sense, this is quite tricky to tackle, I would say. And one approach that has been growing in the last 20 or so years is to try to understand the collective motions of grains when they flow in these dense states by modeling or trying to think in the granular flow as a complex fluid. And when you think in this way, the first question that comes to mind, or the first question that you need to address, is how can you describe the rheology of this ensemble of grains? So, okay, when you think about this, so for now, I gave you this very wide and very large, very broad definition. Let's try to start narrowing down. So when you think about this granular rheology, there are different types of physics that can come to the party, let's say, depending on the particle size, basically. And so if the particles are quite small, thermal agitation can play a role. So these are Brownian particles. And if you increase a bit more, so in the range between 1 micron and 100 microns, you can have like complex interactions, colloidal interactions that may play a role in the collective behavior. And if the particles are larger than typically 100 microns, none of these, let's say, more complex interactions play a role, and you have only hydrodynamics and solid contacts and friction that will govern or will play a role in the macroscopic behavior of this flow. Today, I will simplify even more, and I will neglect the surrounding fluid, and I will just consider dry granular flows where you have only solid contacts and friction in the party, right? Okay, and maybe not the first rheological configuration to characterize the rheology, but today, motivated by all these geophysical flows, I will be using a inclined plane to characterize the rheology of my flow. So let's start with the simplest case. So imagine a Newtonian fluid with a constant viscosity flowing down an inclined plane of an angle zeta. So in this sense, you have that the shear stress is proportional to the shear rate du dz, or where u is the velocity profile. And through this constant coefficient, which is the viscosity eta, right? This I think we all kind of know. And if we consider a steady flow where the thickness is homogeneous through the layer, we can write an equilibrium force balance where you just have simply gravity that balances the shear stress that holds that resists to motion, right? And if you solve this equation applying this boundary condition, no slip boundary condition, and a stress-free boundary condition at the top, you can get the velocity profile across the layer of the fluid, which looks like this. And in these flows of films, it's quite common that the depth of the flow, it's much smaller than other length scales. So it's typically a good idea to do depth average, so you can take average through the depth. And when we do this, so if I define my depth average quantities with a bar on top of the quantities, I do the average over the thickness, and I can get the depth average velocity of these flows, which goes like the thickness to the power 2. So this is for Newtonian fluids. So in a sense, if we do experiments in an inclined plane and we measure the velocity and the thickness, and we know the density of the fluid, we can measure, this is a way to measure the viscosity of the fluid by just measuring the thickness and the velocity of the flow, right? So this is a type of rheometer, I would say. And this is a very specific time because it tells us it's a pressure imposed rheology. So here we are not imposing the volume of the flow, but it's gravity that does the job of imposing the pressure, right? So this is the kind of waters that I will be swimming here. I'll do pressure imposed flow, so inclined plane. And if we try to do the same kind of idea for a granular flows, so if we have now, instead of a Newtonian fluid, if you have an ensemble of grains flowing down this inclined plane, I guess that for you, in the same thing that for me, when I see this, the first thing that comes to mind, it's physics 101. You have a block sliding down a inclined plane. And when we know that the friction that resists motion when this block is moving down, it's proportional to the normal force at the plane. And the proportionality here is a friction coefficient that in this block, it's a constant friction coefficient, right? If we write this, the analog of this in a continuum version, let's say, we can write that the shear stress for a granular flows is frictional. So it's a friction coefficient times the normal stress, which is the pressure. But here, the friction coefficient mu is not a constant. This will be because typically because a granular material is not a block. So you have several grains that are sliding, colliding, and rolling through each other. And for granular flows, a consensus that it's been growing in the last 20 years or so is that at first order, a first approximation is that this friction coefficient is a function only of one dimensionless number, this thing that is called the inertial number, I. And this inertial number, it's proportional to the shear rate, to basically local quantities. So the shear rate, the grain diameter, the pressure that is imposed by gravity, and the density of the particle density, right? So if we do the same game, we write the equilibrium force balance. So you have gravity that balances the shear stress coming from this mu of I P rheology, right? And if we integrate that using that the pressure, it's kind of at leading order is hydrostatic. It goes like OGH through the layer. You basically get that in this steady uniform flow, the friction coefficient should be equal to the tangent of the angle zeta. So you can actually calculate the friction coefficient, the friction within the material by just knowing the slope angle of your flow, right? And I'm not going to go through details here, but if you use these and you input here the definition of I, you can get, and you average through the layer, you can get the depth average velocity profile, which differently than for a Newtonian fluid doesn't go like h to the power 2, but it goes like h to the 3/2. And this is what's called a Bagnode velocity profile. So very good, we can get the velocity profile here. And in the same way, we can compute this I zeta if we measure the U and the H for your flow, right? As I said, this is a first approximation. So this mu of I, this prediction for mu of I, it's at leading order. So let's see how does this compares to some experiments. So what I'm gonna show you here, it's a plot of the thickness of the flow versus the Froude number, which is basically a non-dimensional velocity. And I do experiments for different thickness, and I measure the velocity for each of them. And each cross here represents one thickness and one velocity, right? And what we see at these are results from this paper by Olivier Pliquin in 1999. And we see that at this range where we have data points, this follows quite nicely this straight line, which tells us that Froude is proportional to h. And since Froude is divided by square root of h, this means that the velocity profile goes like h to the 3/2, just as like we got in the previous slide. So this line represents the balance between gravity and friction, where the friction coefficient can be directly measured by the slope angle, right? This is very good. But let's look now, let's zoom in one of these data points and see how do we do these experiments. So basically what we do, we have this inclined plane. These are monodispersed beads, like 160 micron glass beads, and we make them flow with a gate, and we open the gate to a certain thickness, and we let them the grains flow down, right? If we measure with a laser or with a camera the flow, and we do a space-time plot where the y-axis tells you the downslope position and the x-axis tells you time, from the top to the bottom of the inclined plane, you see as the grains are flowing, you see this blurred region here, you have parallel lines, so the flow is moving with a constant speed. And as the material drains, so as the materials, there is not any more material at the top, these flows, they drain out, they go they come to a rest. But when they come to rest, they leave behind a deposit of a finite thickness that is normally called H top. So they give a static deposit at the inclined plane. So if we use this and we go back to our previous diagram, we see that there is a bit of a problem with this straight line because this should not go through zero. So there is when the velocity goes to zero, the thickness of the layer gives a finite thickness H top, right? If we want, yes, go for it.
How's the surface for your experiments? Is it rough? It looked a bit rough. Okay.
Yes. So here, what we do basically is that we impose, this is quite important that I forgot to say, but this is a rough, we make the surface rough by just gluing particles of roughly the same size, at least, of the particles of the flowing layer. But this is quite important because everything that I'm going to mention now, it's about the interactions of the flow and also the rough base. If it's a smooth base, the situation is completely different.
Thanks.
So so okay, we have this static deposit H top. If we want to mobilize this layer, we need to inject material, but we need to get up to a different thickness that we call H start, basically, in order for this material to flow spontaneously. So here there is two things. So first you see that the deposit is different than the point where the material fails. And when it fails, it will search for the next available steady situation. So it will move with this velocity. But as it drains out, it will come back to H top. So this introduces a hysteretic loop in your flow, first of all. And if you look to this linear relation that we get from the balance between gravity and friction, there is a point where you don't have data points. And basically, this is because we cannot generate steady uniform flows to do the same kind of trend of thought that we did so far. And this, what we observe basically, is that at this region at low velocities, you have a zoology of instabilities, the flow is intermittent, and you have everything but a steady uniform flow. So there has been several attempts to describe what's going on in this region. And I'm going to tell you one particular that we did during the time that I was in Manchester, which we came up with an experiment to access the rheology of granular flows in this region indirectly. So we know that we cannot measure directly from this balance, but how can we measure at least indirectly, right? So, and this is through an experiment that we call a retrogressive failure. And basically what we do is the following. So we generate a steady uniform flow through in an inclined plane. And when it comes to rest at the thickness H top, we incline the layer, we incline the plane just a little bit, but not until the layer fails. So we generate a kind of a metastable regime, metastable state. So the layer remains static, but if you introduce any perturbation, such as the one I'm going to show you today, now, you see that there is a wave that is generated and propagate upwards. This is uphill. And this is an erosion wave because it erodes all the static material that was there before, right? I play again. We perturb the flow, and you see that there is a wave that propagates and mobilizes all the static material. If you look carefully to this layer, you see to this wave, you see that this is a traveling wave that moves upwards with a constant speed. And I cannot go through all the details because this would be another 1 hour talk here. But what we can do is that since it's a traveling wave, we can construct mathematically traveling wave solutions that basically connect a static region at the top to the flowing region at the bottom. And since it's connecting a static to a moving state, this depends quite a lot in the form, in the mathematical form, in the functional form of the friction in this connection between the static and the moving branch. And we can test different functional forms to see which one represents better what we measure from the experiments. And by doing so, I'm completely fine to discuss more about that later if you want, but by matching the theoretical predictions of the wave speed with what we measure from the experiment, we came up with a friction law, which is piecewise. So you have a dynamic friction, which is this linear regime that we can measure directly from the balance between gravity and friction. You have also the static branch, where the material is completely static. And this is also a stable equilibrium because you can measure because it is stable. And in between these two, in the region that we don't have steady uniform flows, we connect these two by an intermediate regime, which is velocity weakening. So the friction decreases with the velocity. And this is intrinsically unstable. This is such as like either polymers or gels that you have these velocity weakening regimes that creates this is a very rich source of instabilities, for example. I mean, it's a bit different, but it's unstable in the same way that these velocity weakening are unstable as well. So from these kind of piecewise friction law, what we get is that you have a non-monotonic friction law that introduces this information of frictional hysteresis, because you have coexistence of static and flowing states in the same friction. And this non-monotonic friction law is built by two stable equilibrium that we can access directly, and one intermediate branch that it's unstable, so we can measure it indirectly, right? Very good. This is kind of the rheology of these dry flows in this depth averaged world, let's say. And this brings quite strong consequences to flows. So the first consequence that will be important here is the coexistence of solid and liquid-like phases. So if you draw a horizontal line here in the same friction mu, you can be either static or dynamic. So this creates the possibility to coexist solid and liquid-like states. And this non-monotonic friction law also introduces this velocity weakening branch, which is a very rich source of instabilities that I will show you some examples now. So, okay, this is the kind of the rheological or the rheology of these flows. And now I would like to show you or to discuss with you one or two examples that comes up or that are direct consequences of these rheological behavior of these granular flows.
So
in the first one, yes.
Yeah, so I have a question. So this friction, dynamic friction part, which looks like a linear with u bar by root hg cos j. Is it increasing prime? Is it driven by the gravity in some sense, because your mu is modeled as tan xi, right? So so in the region that you are studying, the frictional coefficient is increasing with the tilt, right? As you increase the tilt, as you increase the angle, the mu is increasing, which is not true for a very large angle. When it's nearing 90 degree, it doesn't matter, the friction will be less relevant. So I want to understand, like, what is this straight line basically means in that sense. Yeah.
So you're completely right that if you go above a certain angle, you cannot get steady uniform flows. So you accelerate. And here, this linear relation here, it's the regime where you can have steady uniform flow. So if you increase the angle, but you increase up to a certain level, friction will adapt inside your material such that it's able to equilibrate this change in the gravitational force. Of course, this has a limit. So this, if you go towards large velocity and high Froude numbers, what you see is that these asymptotes a finite value. If you go above this value, you have only accelerating flows.
Okay.
I'm not sure if this answers your question.
That I understand. Now the intermediate part, which looks like there can be some nonlinearity. At the very small value of velocity, is it approaching some kind of what is the static friction value? Is that like all over the place? I can see different crosses. Or is it like a fixed value that you can get when in whatever path? So you are talking about hysteresis. What is the static friction that all the hysteresis approach? Is that a converging value? Is that a different values depending on your?
So basically, for example, the static friction is a multi-valued friction, because it can, for example, if you think about a pile of grains, you can increase the angle of the pile by quite a lot before it fails, right? So the static friction can assume different values, but there is a maximum value above which you cannot hold static. So the static friction you can characterize until the maximum value, and this you just do by you introduce material in your inclined plane, and you introduce the material static. When it gets to a certain thickness, it will fail. And this maximum thickness that material can hold static defines your maximum static friction.
Understood. Understood. There are different parameters. Okay, good.
Yeah, sure. There are different parameters. I'm not showing here exactly the functional form of these because these would require like 2 or 3 slides, but it's just the grasp, let's say, the qualitative image that we discussed. But okay, so very good. So let me discuss a bit now one example with a very simple problem that this particular rheological behavior comes into play in many different ways. And this is just let me show you this experiment. So this is an experiment in the US Geological Survey where you have this 82-meter long inclined plane. And here at the top, we will release a mass of a mixture of water and gravel, right? And let it go. So here it comes. When it will cross this gate here, it will enter a flat runout zone. And when it enters, it will throw some colored particles as traces, right? So if we look from the top, what we see here is that as soon as the material enters this flat runout zone, it spreads out a little bit, but not too much, and the edges of the flow kind of solidify and confines the flow to its interior, to a flowing channel in its interior, right? Of course, here the traces can be used to kind of see the trajectories, and I will use these at the end of the talk if I have time. But this allows us to compute trajectories of depending on where you enter the flow, where you're gonna die in the flow, or where you're gonna be deposited, right? But this is kind of a very interesting thing because the flow doesn't spread, it solidifies and spontaneously it self-confines, right? So this is what we call self-channelization, and this is widely seen in nature. For example, in pyroclastic flows, you see these very elevated walls that confine the flow in its interior. You see these from a point source in a snow avalanche that you can have quite parallel walls here. And you see in these flows, which are rock falls on the surface of the moons, which, in my opinion, it's the closest we get from the lab experiments. And this, for me, it's very interesting. And in this geophysical context, we call that these static walls, they are called the levees, and these levees form spontaneously and confine a central flowing channel in its interior of parallel walls. What I would like to discuss with you now is why this happens. So let's go to the lab. And in the lab, we use very monodisperse grains of sand, and we make it flow down an inclined rough plane that we make it rough by gluing some glass beads, right? So if we look for the global picture here, you first have the front that propagates downslope continuously. Eventually, a steady state is reached where nothing moves. So if you continue to inject material, this morphology will stay there for days. And this is very particular of granular flows. If you do the same thing with a Newtonian fluid, what you see is that the width of these channels, they get wider and wider as you go downslope, right? And if you stop the inflow, all the material that was flowing in the middle, in the center of the channel, it will drain out and leave behind this fingerprint of the flowing channel, as you see here. So it leaves behind the fingerprint of the channel that was before. So first of all, why do you have these parallel walls? This is very peculiar for granular flows, let's say. And in a more practical way, it's quite, I would say that it's a question for like geologists or engineers, like what sets the width of these channels? So how can we infer, for example, properties of the previous flow by just measuring the deposit, for example? Because when an avalanche is happening in a mountain, nobody wants to be there, right? So we want to have to be able to infer properties of the flow by just measuring the deposit, for example. So this is the global picture. Let's look a bit in more detail. So this is the flow, the front passes. And even when the kind of steady state was apparently reached, I'm going to move faster here. So you can have some kind of readjustment at the border, which kind of test if the boundary between solid and liquid-like phases are in the right place, right? And if we look at the border, you see that there is a very rich dynamic here that sets this boundary or this interface between the solid levees and the central flowing channel. If we change the mass flux, I just put my finger on the funnel, for example, and you decrease the mass flux, the channel adjusts and it retracts back and finds a new equilibrium state accordingly to this new mass flux. On the other hand, if we increase the mass flux, we erase completely the history and we get a new steady state, which is now associated with this new mass flux, right? So what we can see from here is that you do have a very well-defined equilibrium state for these channels, which depends on the slope angle and on the mass flux that sustain the flow. This is not completely dominated by history. This is actually, you have an equilibrium state that is fixed by the parameters of the flow. How can we understand this and why does it happen? So to do so, to try to model it, I'm going to use a depth average model where the flow is basically governed by a mass conservation. H is the thickness of the flow and U bar is the velocity profile. And you have a momentum balance where you have the inertial term, so the acceleration of the flow. You have a pressure gradient. You have a source term, and this source term basically takes into account gravity that makes it's pulling the material downslope and friction that holds the material back, right? And here, when you do this depth average process, you have a higher order term that brings up a viscous-like, so this is like a Laplacian-like term, that it's like a viscosity term to your momentum balance, right? If you think about lubrication theories, for example, normally it's neglected inertial terms and this term, this higher order term. If you think about shallow water equations, it will just, they will neglect this higher order term. So here you need to consider, I'm going to try to explain why do we need to take into account these friction high order terms, etc. And where does the rheology of the granular material comes into play? It's in this mu b here. It's the friction law that we discussed how to characterize this non-monotonic friction law. It comes as a function of the thickness of the flow and the fluid number. So the first thing that I will do here is I will solve these equations using a finite volume numerical scheme. And this is what we get. So on the left, you have the plots of the velocity profile. And on the right is the thickness profile of the flow. So here, what we see, if we plot something like a cross-slope profile, we see that initially, these orange dots, everything is mobile at the front. But as soon as the front passes, the edges of the flow solidify, these blue regions here, and you approach a steady state velocity profile. In the same way, if you look to the thickness, you have a uniform thickness when the material is flowing, but as it drains out, and it will do now, the material in the center drains out, so it leaves behind these super elevated levees at the borders and a smaller thickness in the center of the channel. So this qualitatively, it's what we observe in the experiments. But let's see if we can understand a bit more what sets these equilibrium states of these flows. So to do so, this is quite simple. So it's a uniaxial. So we want things that don't depend on time and don't depend on the downslope position. When we put this in mass conservation, we get that there is no lateral motion. So everything is moving downwards, right? You have no motion laterally. If we input this into the Y momentum balance, you get that the thickness in the central channel, it's uniform. Where it's moving is uniform. And by putting this into the downslope momentum balance, you get an equilibrium force balance, which is an equilibrium between gravity, friction, and these higher order lateral viscous stresses. that governs these equilibrium states. And this, if you reorganize, this is just a second order boundary value problem, where you don't know the thickness of the flow and you don't know where's the boundary between static and liquid states. But luckily, what we have here is that we have enough boundary conditions and we have a constraint that relates the thickness, the velocity, and the flux, because the flux, it's a constraint, we know how much material we are putting into the flow. And with this, we can compute the velocity profiles for different fluxes, right? And the first thing we do as a sanity check, let's say, is to see if our numerical simulations is converging to this solution, and is indeed the case. So this is the white solid line that I show you here, and the dots are the numeric full time and spatially dependent simulations. But this is, okay, this doesn't mean that the model works, but at least the numerical simulations are indeed converging to the steady state exact solution. But let's see if we understand why we get these profiles. So if we look, this is the equation that governs the steady state. And on the right here, I show a velocity profile, typical velocity profile from a given flux, 100 grams per second here. And so what we get is that you have in the central channel that moves faster and connects to the boundary where the velocity is 0 through this kind of boundary layer that the velocity goes from the maximum to the minimum, right? If I draw a friction as a function of the fluid number that we had before, so we had this non-monotonic blue curve. This is the intermediate regime. This is the dynamic friction, right? If I draw a horizontal line that represents the slope angle, so the gravitational force, I have three equilibrium actually. One is static, but I have two moving equilibrium. One is with this velocity u star, and the other one is in the dynamical branch, this u0. So this one and this one. And this defines kind of two regions in my flow. Very close to the boundary, in this yellow region here, where the velocities are lower than u star. Friction, the blue curve here, it's higher than gravity. So the material would like to stop. But this higher order term, this higher order viscous term, they act as a driving force that accelerates the fluid and enables the flow to reach an equilibrium state that satisfies this equation. Closer to the center of the channel, what you have is the opposite. So friction now, it's smaller than the gravitational force. So the fluid, the flow would like to accelerate. But these higher order term, they act as a dissipative term. So they hold the material and enable this steady state to be achieved. So this boundary layer that enables the velocity profile to be constructed from a maximum velocity to connect to this static solid state at the boundaries is due to this interplay between hysteresis that is incorporated by this non-monotonic curve and these higher order lateral viscous stresses. So it's the interplay between these two terms, these two stresses, that enables this boundary layer to form, and therefore the connection between liquid and static states. Let me compare now the results that we get from this model with some experiments. So first, we compare with flows of glass beads, where we measure this. I mean, these experiments were done by Felix and Thomas in 2004. And here we compare the thickness and the width of the flow for each mass flux, as well as the full thickness profile that they measured. So we see that although the thickness of the flow, it's in a reasonably well agreement, the width we seem to overestimate with our model. And if you ask me later, I may have some reason for that, but I leave for the questions. And this, we see that in the same way that the width here, the thickness of the flow we can predict quite well, but the width of these channels for high enough fluxes, we seem to kind of overestimate. This is not really the case when we compare with angular particles of sand, where we have a much better agreement for the thickness, for the width, and for the velocity profile of these channels. And these may be related to the interlocking that glass beads are spherical beads, so they have some kind of slow creeping, lateral creeping that widens the channel. And that's why this fully steady state theory, they predict a wider width because the system didn't yet reach this fully equilibrium state. This is a hypothesis, right? But what this theory tells us also is that if you decrease the velocity here, if you decrease the mass flux, the velocity in the center of the channel decreases. And there is a point where friction will switch from the dynamic stable branch to the intermediate unstable frictional branch. And what this tells us is that at very low mass fluxes, these stable solutions, they become unstable. What does it happen there? So if we go to the lab again and we do experiments. So here is the same configuration, but I change the mass flux that I inject grains to a much lower mass flux in the zone where the theory tells us that it's unstable. And the situation changes completely to this scenario. So now we don't have the front that propagates continuously, but we have this. So basically, there is a front that propagates until it sees the empty bed and it sends back this deposition wave that brings all the material to rest until the source. Since we are still injecting material, this pile goes up, increase in angle until it goes above the maximum static friction. And then it sends again a new pulse. And these pulse, they propagate like solitons, like solitary waves along this static deposit until it sees again the empty bed when another deposition wave will be sent backwards until the source, right? And what is interesting here is that we don't need any extra ingredients we just need to decrease the flux, and it seems that the physics is there and we can reproduce what we see in the experiments with our simulations. So we see this, when the flow sees the empty bed, it sends back this erosion wave that fails periodically. And what we see, if you measure the velocity profile and the thickness profile in the center of each one of these channels, so here I show you in blue is the thickness and in red is the velocity. So when the material comes to rest, the only thing that is moving, it's in the pulses, so in the solitary waves. All the rest is completely static, as we see here in this blue region. So these are really solitary waves that propagate across the static deposit, right? And another thing that is funny is that these solitary waves, they become quite periodic, both in the experiments and in the numerics, and with a very well-defined period. So in these periods, we didn't prove that, but it might be related to this maximum static friction that the pile can sustain static before it sends another pulse, right? So with this, I think it's come to my time. I don't know, maybe it's my time. I had something more to show, but let me conclude at least this part. So in this, what we see so far is that we have this non-monotonic friction law for dry granular flows that incorporates frictional hysteresis and allows this coexistence of solid and liquid-like states of the flow, right? This non-monotonic friction law, it's made by two stable equilibrium, the static and the dynamic branch, which are connected by this unstable velocity weakening regime. This hysteresis plus these higher order dissipation terms that also comes from the rheology, they are key to predict these pattern formation, these self-organization patterns where you have coexistence of solid and liquid states. And also, because you have this unstable velocity weakening branch, this is also a very rich source of instability, such as on this case that I showed you on the right. So only in this very simple case of a point source of grains flowing down an inclined plane, you have so many consequences of this peculiar rheology that can lead to these very interesting self-organization and instability patterns. And what is nice, I mean, what is interesting at least, is that I'm going to show you a video here that is very old. But this is a flow, it's a debris flow here that I took from the internet. So you see that there is a pulse that comes, and this is a mixture of large, small particles. But you see that at some point, the flow would come to a rest. The flow comes to rest when a new pulse comes in here, just like we saw in this last example that I showed you in the inclined plane of monodispersed, only dry flows, right? And we see also if I advance here a bit, we see also these kind of solitary waves. You have a static base, a static bed, you have a pulse that comes up, mobilizes the initially static grain, and passes by. Everything comes to static again when a new pulse comes back. Of course, so this is very nice because this depth average model can predict this kind of phenomenology. Of course, here there is one extra thing that I don't have time to speak, but I hope next time I do have, which is how can we incorporate when you have particles of different sizes, for example, how these affect the flow, right? I will just, yes?
Sorry to interrupt you to close to your conclusion. I mean,
No,
anyway, I don't know what Leah thinks, but I am totally amazed and in love with your videos and experiments, and you seem to be too. So I would not like you to interrupt this presentation. Anyway, it's recorded, so people can always come back and watch it on YouTube. So I guess that it's really up to you at this point. But I do have a quick question based on your
Yes.
about your previous, I mean, not about segregation, of course, but about the inclined flow. And it
Yeah.
may be not very important, and it may just be a detail. I actually need you to go probably to the first slide of this section of experiments, because it was even before. Yes, probably here. Can you? Is it the same? The only? Yeah, go ahead. I think there is another one coming. Yes. Okay, here. No. Well, it was the figure on the right on this slide. Exactly. So, is it me, or you can observe these lines on the bed? These kind of parabolic lines going upwards, though. They seem to go
Yeah.
upwards. Why?
Yeah. So if you look, I'll tell you that the short answer is I don't know, but
Okay.
I might have an indication, right? Because the thing is that what we are doing here, it's a continuum model. This seems to, I'm not sure if it's related to that. But if you look to the video, and when you see that is draining down on the stop.
Yeah, okay, I've seen that. I've seen what you're seeing. Like it definitely has this. But actually, I noticed that you have exactly the same in your simulations.
Yeah. So you see this. You see that you have this kind of V-shaped tail.
No, I mean,
that moves up.
it kind of. I wouldn't say that it makes sense. I don't know, but I would predict it based on, I don't know, experience in observations. I don't know. I was just thinking why, because at the center the velocity is higher. So I don't know. I don't know the answer. I don't know if it's important, but it's there.
Yes, and these actually we see this kind of tail. If is draining, or if we change the flux, there is a wave that connects the two states, and we always see this kind of tail, this V-shaped like tail. To
Is
be
it
honest, we didn't.
maybe
Yeah,
because
sure.
it's you have a decrease. It's not a. I mean, it's maybe a full stop of the input flow, but you of course have some transition, and given that you have less and less material, probably the depth is decreasing, and so it's also self-channelization in detail somehow. or the boundary that stops actually decrease. I mean, I don't know how you want to see it, but the width of the moving part decreases because the
It
depth
could be,
the depth is
it could
decreasing
be,
there.
it could be that you have, as you say, it could be that the parts which are connected to the elevation, they keep more or less the same thickness, and therefore they will move, although they are close to the boundary, they will kind of move. And in between they kind of deep down, and as they deep down, they will move slower, and that will kind of, as you say, it can explain that. It could be an explanation, and then you just have these slides, they kind of drain out of these things, where at the boundaries will just have a friction that is like a solid friction.
Yeah.
It could be an explanation, yes.
By the way, it's very nice, extremely beautiful. Yeah,
Yes,
you had a
so no, I
Yeah.
had a couple of things more, but I will not, because I will need at least 10 minutes more.
Okay, because my
but I will-
questions was about like not the last video that you showed, but the one with you have the I don't know what is exactly going down, but like you have rocks and so on, and you have
Yeah.
actually not really a segregation, but you can see that the bigger rocks they go up, so you have a Brazilian effect, and then they go down again, and then they slow down. The thing I thought it was because there was two sides
Yeah.
in the flow that it was doing this solitary wave. So I don't really understand why does this thing. Really, I have no idea. On the video,
okay.
like the first video that you showed at the end.
So the thing is, for these solitary waves, we don't need segregation to happen, such as I'm showing here.
Yeah.
Right? The segregation will help, in a sense, will give another mechanism for change the local friction, and therefore you have more increasing friction at the front where large particles will accumulate.
Okay.
But you actually don't need this, because basically what you see here is that in a wavy, in a hand wave explanation, the velocity in the center line of these channels, because the mass flux is so slow, it will be a velocity governed in the intermediate friction branch. And this is unstable. So this, what it does is that you basically have a snap-through instability that brings material to the static. Because you are close to the static branch, it brings the material to rest.
Okay.
And as the material comes to rest, it does kind of hydraulic shock, in a sense, that sends back this information. It's like a wall that is created, and it sends back this wave until the source.
Okay. Oh, wow. And also, whenever it comes to very big width, it seems like you have some wrinkling on the sides. And I was wondering if you have like just another instability on the side that is like a wave thing, and that's why it deviates from the model. I don't know.
You mean
like
in this case, or?
Yeah, this case, but like the bigger the higher flow rate, then you have like some wrinkling on the top and also on the side, and it increases with the size of the flow rate, and then you can see on the points, the data point, and it deviates from the model. And you said like you have no really ideas, but I was wondering if you looked at the waves on the side, and if there is no one characteristic length at which then it's another state. I don't know.
Yeah. So these, these waves that we see in the surface, or even in the parallel walls that we see there, these can be very high frequency raw waves, because the Froude number is above the critical Froude number to have these waves, but they are not enough to destabilize or to enlarge the channel, right? So these are very high frequency waves. And what was the second question? And then
for the one on this side, then
on the side, you really see. So if I go back here, and if I show just the boundary, you see that there is also some kind of like, I don't know if it's my eye, but I see some kind of waviness here as well, that you have this kind of very rich instability. With some colleagues in Manchester, we started doing some instability analysis on this kind of flows, more like two-dimensional instability analysis to see if we can get this. But it's not, we didn't get to the end yet, so we don't have.
Okay. We'll see that in the future.
It seems that you have a very periodic instability here. But if you look closely, or if I put the mouse here, this doesn't change the mean position of the interface between solid and liquid states.
Okay. Well, we'll see that in the future. Okay.
Yes.
Thank you. Is there any other questions in the audience? Because I'm sorry, I rushed with my questions, but if there are any questions, you can go for it. I don't know if you can see the chat here.
I cannot.
No.
I don't see any question in the chat.
Okay, well, then if you have question, I'm sure that Francisco, you will answer to them by email, something like that. Thank you very much. It was a very wide talk, many things.
I mean,
I would love to see the end of the talk. I don't know if you have time to do that.
Do you both have 10 minutes?
Yeah, I have 10 minutes. I
Do
would love
you,
to see
Chico?
it.
Yes, I do have, yes.
I mean, I'm all in. Let's go.
Yeah,
let's go. I just tell you a bit more, which is going towards more realistic.
Anyway, when we say 42 minutes is minimum.
Okay. I did. That's why I prepared. That's why I prepared more.
Okay.
So the idea here is like, okay, how can we, if we have particles of different sizes, how does it affect, or what is the pattern that it forms within these self-channelized flows, right?
Yeah.
And what previous experiments tells us is that you have some kind of organization. So these large particles, they go to the front, they form these very bouldery like front. But this, if you see inside, this is a self-channelized flow here. So you see this is a channel that in this paper, they put some kind of resin and they solidify the flow and they cut in the middle to see where the large red grains are and where the small blue grains they are. So what we wanted to see here is that can we predict also this self-organization when we have particles of different sizes within the self-channelized flows, right? And basically, this is when you have particles of different sizes, you will have this phenomena, which is called particle segregation. That is basically, in a very short comment here, if you have a walnut, for example, and you fill in with peanuts, for example, and you shake, which are smaller, so if you shake, what you see is that the large particle up comes to the top, right? And this happens not only when you have one particle, but happens also in a bulk scale where you have 50% large, 50% small. And you see that even when you start in a configuration where you are inversely graded, so you have all these large particles at the bottom, and you start applying a shear to them, they segregate, the large particles segregate up and the small particles go down. This particle segregation, or Brazil nut effect, people also call it this way. So what we wanted to say here is like, okay, can we learn a bit more from what we learned from the self-channelized solutions if we put particles of different sizes? So let me explain what we do. So first, we generate a self-channelized solution, just like I explained in the previous part. And because we know in my first slide what's the shear profile, we can construct the full three-dimensional velocity field. So not depth averaged anymore, but now you have an in-plane velocity field, but you also have a vertical structure of the flow, right? And this, we're going to impose this velocity field, and we're going to inject particles of different sizes at the back of this flow. And to model the particle segregation, what we do is basically, we have here bidispersed flow. So you have a concentration of small grains, phi s, and a concentration of large grains, phi l, which gives a closure relation. So both of them when you add up should go to 1 because it's everything you have. And to govern the conservation law, the transport of these grains, you write down this kind of conservation law where you have the change in volume fraction of one of these species. It's given by advection by the flow, by segregation. So large particles should go up and small particles should go down. And in the general case, you also can put some kind of diffusivity if you want. Here, I'm going to think in the simplest case, where you only have advection and segregation, and you don't depth average, but you assume that the flow is shallow. So you neglect the terms which are not important when the thickness of the flow is much smaller than other length scales. When you do this, you get this kind of equation that the segregation term, which is this last term here, depends on a function FSL, which is the velocity, segregation velocity. And this segregation velocity, I give the expression here. It should scale like the shear rate. So if there is no shear, there is no segregation. It should segregate, it should scale as R, which is the ratio between the grains. Because if this ratio is 1, there is no segregation. So this velocity goes to 0, right? And so we impose the velocity field and we solve the segregation equation to see what happens. Let me show what we get. So this, we have the self-channelized flow, and we inject here 80% small particles and 20% of large particles. Large particles are represented here in brown, where the yellow is small particles. So what we see is as they enter the flow, if we look first to the left column, we see that large particles immediately segregate to the top of the layer. And because the flow is faster, they are transported to the flow front and they accumulate at the front, as we've seen in the Rio flow, for example. As they arrive here, they are overrun by the front because they come down, so the velocity decreases and the front overruns. And in between, what you have is that between these the large particles to the top, the small particles, they go to the bottom and they accumulate, they populate the center of the channel. In between regions of large and pure small, what you have is that you have this blurred light region, which is a breaking size segregation wave, where you have this kind of coexistence between large and small particles, basically. But this vertical segregation also leads to a secondary mechanism where, as the particle go to the top, they are also, when they come to the front, they are transported to the sides, and you have this accumulation of large particles in the levees, as you see these black, these darker regions at the outer side of the levees. So even though you don't need size segregation to form these self-channelized flows, because these large particles, they go to the top, and after they are transported to the sides, these segregation, these form a kind of a carapace that protects and creates some secondary mechanism to resist these channels, to make channels more resistant. What we can do also, since we have the full three-dimensional velocity profile, we can compute the trajectories of each type of particle. So let me show you here. Well, how do we do? We just solve the X, Y, Z equations of motions for each type of species, large and small, new here. And the velocity profile, we know because we know the velocity everywhere. So if the small particles which enter in the bottom part of the flow, how do they live within these fronts? So if they come to the front at the center line, they circulate until they come back at the center of the channel again by these red curves here. But if they enter the flow at the edges of the central channel, they circulate and they are deposited at the levees. So although you have large particles at the levees, you also have a layer of small particles that are deposited within the static regions. On the other hand, for large particles, you have completely the opposite. So what you have is that the particles that enter the flow at the edges, they have very short-lived life. So they enter the flow and they are overrun they slow down and they are deposited at the top of the elevation. But the particles that enter in the center channel, a bit off-centered, you see that they come down, they do a kind of a swirl before they are deposited at the outer edge of this elevation. So this is kind of I just wanted to show this because this is a kind of an uncoupled model that we just impose a velocity profile to solve the segregation equation, but we seem to get, at least qualitatively, the same morphologies that we get from the experiments, right? So large particles form a carapace that extends over the central channels and the outer parts of the levays, while the small particles concentrate at the center of the channel and the inner part of the levays. And this information here of the small particles at the inner part of the levays can be, we are not sure, but this can bring to a secondary mechanism, because normally these geophysical flows, they are observed in much lower slope angles than what we see in the lab for dry flows. So maybe this is because you have these fine lines of small grains that create some kind of lubrication or a lower friction close to the solid liquid boundary that can allow the material to flow. And as I said, particle size segregation is not required, but it can indeed feed back to enhance the mobility and the strength of these levays. So now I finish here, and I would just say that I would like to thank Nico, Chris, and Andrew, with whom I did this work in Manchester. Thank you very much.
Thank you.
Thank you. Thank you very much. It was a very nice talk.
Indeed.
Yeah. Is there any question in the audience?
Well, I don't really have a question. It's more a comment. In the sense that, correct me if I'm wrong here, but if I remember well, segregation really depends on the kind of motion you impose to the granular material, right? Like if you, as you said in the Brazil nut, how do you call it? The effect. Thank you. You agitate up and down, and that's also a very effective way to take out the chocolate from a cereal box, by the way. So if you want to teach physics to your kids, that's a very good way.
Yeah.
But if, for example, let's imagine you have, it's a bit weird, but let's imagine you have a 2D plane of grains and it's homogeneously mixed, and you just shake the bottom. If I remember well, exactly. I mean, what do you mean? The big particles would go down, right?
Well, Francisco, sorry.
I think that in that case, I think that the big particles would go down, if I remember well.
So this, I mean, no, go on. Sorry.
No, that's it actually. I was just wanting to know what you think about it, and also, do you think it? I mean, here the flow is very complex, so there may be different mechanisms for segregation, I guess.
So this is actually something that is still the origin of segregation is still something that it's under debate, right? But there is a paper by François Guillard, Olivier Pouliquin, and Yoel Forter, where they do DM simulations, and they show that the segregation can be induced, and there are other experiments as well, but they can be induced by gradients either in pressure or gradients in shear stress. And these two effects, they have different roles, let's say, where the large particles go or the small particles go. So for example, if you have an inclined plane situation where the large particles go to the top because they go against the pressure gradient, in a vertical chute, for example, where you don't have pressure gradient, but you have walls, so you have a shear stress gradient, they go to the opposite side. So they go to the center, the channel. So this really depends, and how exactly these two terms, this shear gradients in shear stress or gradients in normal stress, they drive segregation is still something that at least I'm not completely aware if we have a final answer, but
Okay.
I would say that we don't yet.
I don't think either. Which is good, which is good. That leaves us something to discover in the future.
Absolutely.
That's why they should
Oh,
hire us, right? That's the reason.
Absolutely. I agree.
well, then I think we can thank you for the talk. And if you want
Thank
to
you very
stay,
much.
we can have a little chat if you have time. But
Sure.
thank you. I'm going to stop the recording for now because it's a very long video for YouTube. So bye, YouTube.